Welcome to the lesson on section 10.2, Eulers method. In this lesson, you'll learn how to use Eulers method to approximate a function value of a particular solution to a differential equation. Thinking back to everything you've learned in this course, recall that we usually learn both exact and approximate methods for how to do everything, such as finding the slope of a tangent line, finding the area under a curve, evaluating a limit, and so on. Today, we'll look at an approximation method for solving differential equations, and in the next lesson, we'll look at a method for finding an exact solution to certain types of differential equations. In my first example, I'll demonstrate how to use Eulers method to estimate the value of y when x equals 3/10 for the differential equation y prime equals 1 plus y if y of 0 is equal to 1. So here's the idea behind Eulers method. First, the solution we'll approximate passes through the point 0, 1. A step of point 1 means that I'll use the slope at that initial point to connect to another point at x equals 1/10. My next segment will connect to the point where I just left off using the slope at that point, and the segment will end at x equals 2/10. Picking up from here, my next segment would go from x equals 0.2 to x equals 0.3 using the slope at the point where I just left off. Here's how I'd suggest keeping track of your calculations. I'll set up a table with columns for x, y, the slope y prime of the tangent line, and then using the tangent line to find the point at the end of the segment. We're given an initial point, 0, 1. Use those values to calculate the slope of the first segment. Then write an equation for the line that passes through the point 0, 1 and has slope 2. This segment has to end at x equals 0.1 because of the step. Plug in 0.1 for x to find the endpoint of the segment. So the endpoint of the first segment is 0.1, 1.2. Write this in the next row because it begins our next segment. So use these x and y values to calculate the slope of the second segment. Write an equation for the line that passes through 0.1, 1.2 with slope 2.2. The x value at the end of this segment is 0.2. Plug this into the equation of the line to find that the y is 1.42. Plug this into the differential equation to find the slope of the next segment, 2.42, and use the equation of the line through this point and having this slope to find the y value at the end of this segment. Notice that the part in the parentheses here matches the step every time. This happens because we're using the left endpoint of the segment to write the equation of the line and plugging in the x value at the right endpoint of the segment to calculate the next y value. Our goal was to find the y value when x equals 0.3, so this makes our answer 1.662. Next, I'll use Eulers method to estimate the value of y of 0.8 for the differential equation dy dx equals y plus x squared if y of 0 is equal to -1, using a step of 0.2. My table has columns for x, y, y prime, and the tangent line. Starting with the initial point 0, -1 in the first row, plug these into the differential equation to calculate the slope, and use this information to write an equation of a line. The x minus 0 part of the equation will always equal the step after I plug in the next x value. So I've already just replaced that with a 0.2. So this makes the next y value -1.2, and so on. If you'd like to finish this one on your own, press pause now and then continue after you've finished. So I end up with y of 0.8 equaling -1.95168. This concludes the lesson on section 10.2, Euler's method.